Warning, this screencast will blow your mind completely. It may possibly be the greatest thing you ever watch in your entire education. So, you have been warned. We're going to look at electric fields and it's quite important. So, the basic idea of an electric field is you have two charges separated by a distance r. Okay? Now they're 2-point charges, or two charges that can be considered point charges, and the force between them, F, is equal to K Q1 times by Q2 all over r squared. K is equal to 1 over 4 pi epsilon 0. So what does that mean? Well, if you double one of the charges, the force between them will double. If you increase the distance between them, the force will decrease. And K is just a simple constant of proportionality. So, obviously, Q can be positive or negative, but if you take two positive charges, as you know from basic physics, possibly studied when you were very young, two like charges will repel each other. So in this case, the force is positive. A positive force in a radial direction will mean that the forces are intended to move outwards. Okay, if the forces are moving outwards on each other, forces are two negatives as well. Two negatives will do the same. Okay, a negative and a negative will cancel out and give you a positive charge. So the only thing that you can change is you can make one of the charges now negative, and in that situation, when you make one of the charges negative and the other one positive, and you've got then opposite charges, you will bring them in because you will have a negative force. And when you make the force negative, then you're looking at a negative movement in this radial direction, and so you'll have a force inwards towards the center of the radius. Okay, so that's why things repel and things attract. It's because of Coulomb's law. Now, when we look at electric fields are defined as the force exerted on a tiny positive charge by another charge. So if I draw here a charge Q1, and I've got another charge here Q2, and they're separated by a distance, let's be really imaginative and call it r, then the distance between them will obviously affect the force. The question is, what force will be affected, or what will the force on this one be? Okay, well, the field strength is commonly, in layman's terms, defined as the force per unit charge. Simple enough. So we take our equation for force, or E is equal to F over Q. Okay, now this concept of field strength is not a new one. Okay, field strength is usually force per unit quantity. So E is F over Q. Let's just have a look at F again. So we've got, I'm going to call this Q2 because I want to know what is the field on Q2 created by F1. So we have K, Q1, Q2 all over r squared divided by Q2. So in this case, obviously, the two charges cancel, and we have E is equal to KQ over r squared. Notice, I've left out the 0 or the 1 here, okay, because we're just considering it now to be, in general terms, what is the field created by that. Okay, now you can vectorize all of this. That works because obviously there is a direction. So I'm going to go back and I'm going to add my direction. I'm going to add my vector. So, electric field lines. Easy enough. A field line shows a line of force. So, I'm going to start off with a charge here. Again, going to label it Q. And line of force. Now you need to think line of force per positive charge. So if you imagine that I put a tiny, now electrons in all of the films are always green, so let's stick with sci-fi. Let's put a charge here. Okay, this is not an electron, this is a positive charge. And now I said electron, and I'm still saying electron, but don't think electron, think positive charge. If I put positive charges here, what will they do? Well, Q is positive. You can tell it's positive because I put a positive next to it. And it will repel outwards, okay? Sorry if you're currently being deafened by the noise from the fan of my CPU. That'll happen. So, positive charges will repel. So, what is a field line? Shows a line of force. You want to think field lines? Think, what would a positive charge do? Okay? Now, obviously, you can change this around a little bit. Okay? You can change the field to a negative field. Okay? And then everything will then magically want to go inwards. Inwards. Because a positive charge would feel a negative force and that would move it in. Okay? So I know you're probably thinking, ooh, what a pretty mangly diagram. So, we just undo some of that. Boop. Boop. Then we can have a look at it again. We can compare it. So we go Q is now a negative. So I'm going to put negative next to it. Okay, if you put these positive charges here, they would shoot in. Positive charges, they shoot in. Positive charges shoot in. Okay, so positive charges would shoot in towards the negative because of the attractive force on them, as defined earlier on when we went through Coulomb's law. Easy enough, right? Indeed. So, the next thing I want to look at is electric potential. Okay, now a potential is defined as, and certainly in this case, the energy required to bring a charge from infinity, can't spell, to that point. Okay, so here we go. Here is a charge, Q. Let's make it positive. No, let's not care about its charge. Let's just call it Q. So here we have, right at the far edge of the screen, so as you can believe me, another charge here. I'm going to call it little q. That's our point charge, and we're going to bring it all the way from the edge of the screen, which isn't actually infinity, but we'll say it is for now. And we'll bring it into R. Okay. Now then, energy is equal to force times by distance. And this is the part where those of you that don't do A-level maths are gonna hate me. And if you are doing A-level maths but haven't done this yet, Okay, so we bring a charge in to this point R. So the electric potential, let's not confuse us with fields, let's call it V for electric potential, is equal to, let's bring it in from infinity. Force times distance is actually the integral of a force distance from infinity to 0, or infinity to R. Okay? So, let's integrate. So, the force per unit charge, okay, if we just have a charge of 1, then what you're left with is my charge of 1, K, Q, times by my charge of 1 over R squared. Now, the first thing I'm going to do now is get rid of that 1, because I don't really want it, because it's just going to mess me up. We've got KQ over R squared. Now, if we look to integrate it, okay, then we're going to integrate that with respect to R, so integrate it dr. What you're left with is KQ R to the minus 2, these are constants, so let's integrate those with respect to R between infinity and R, and we have KQ R to the minus 1, okay, divided by minus 1. So, integration. Integrate this, the power increases by 1, and we divide by the new power. New power is minus 1. Okay, so we're looking at between the points of infinity and R. Where can this go next? Well, we can then actually evaluate it. So V is equal to that. So V, let's split the page so as you can see what I'm doing when you look back. We have K, Q, need to put a minus in there because that's that minus 1 here, minus KQ R minus, sorry, power of minus 1, let me just redo that, let's tidy this up, KQ over R minus KQ over infinity. Now I know exactly what you're thinking, anything over infinity is 0, so minus infinity, nobody cares. So V is equal to minus KQ over R. Happy days. Okay, so now then, just to be a little bit pedantic, the electric potential is commonly denoted as minus, okay, but I neglected that minus at the start. Why did I neglect it at the start? Because I didn't want to carry it all the way through at the end. Okay, so here's this concept. What we did was the energy required to bring it from infinity to this point. Okay, but actually the energy that it's got at this point is the energy that it has to get back to infinity. So we could reverse everything, but we're not going to. I'm going to put the minus in at the end, and I'm going to change that to a positive there. Why? Okay, now what I just did was I just showed how to calculate the potential using calculus, but here's a simpler way to look at it. The potential, okay, is a form of work. Now if work done is force times distance, okay, the potential, V, is force per unit charge times by the distance. Now the reason why I say it's the force per unit charge is the potential, if you think about it, is the potential energy that if you brought a charge to that point in space, that it would have that potential energy to do whatever, okay? Now, if you put a positive charge here, it's got a positive potential energy, and it could potentially fly outwards, and it would fly outwards because the two positive charges would repel. So, to look at the simple way to do this without needing any calculus, you can just take your F over Q, which is E, and multiply it by the distance. The distance is just going to be R. So what you have then is just V is equal to KQ over R squared times by R. So V is KQ over R. All of a sudden, it looks pretty easy. Okay, so that's the easier way to look at it as well. And you may prefer that way to the other way. Okay, I hope this helps. If you need to watch the video again, do so and take notes on it, look back, but hopefully everything that you see, if you look at it a couple of times, you should understand it.